One of the more interesting techniques that you can do when evaluating the derivative is using something called logarithmic differentiation. Logarithmic differentiation is a way of kind of manipulating what you're doing to make your derivatives a lot easier. What it does is it says, okay, let's say I've got a function, and let's say it's a differentiable function, and it's positive. So those are kind of some key pieces. We can say that, all right, I've got y equals f of x. So if I take the natural log of both sides, again, if it's positive, this is valid. If I take the natural log of both sides, and then I take the derivative of both sides, then the logarithmic differentiation will say, okay, this is 1 over y times the derivative of y, so y prime over y. And then the derivative of this is 1 over the function times the derivative of the function. So then I can move that y over to this side to get the derivative y prime in terms of this. And since you know that y is f of x, this actually cancels and gets us what we're looking for. Okay, so you say, okay, well that looks like a lot of work to just take a derivative. Well, the reason we do this is because this kind of hides some of the detail of what's happening. Doing some examples shows you why this is a really interesting technique. So this isn't exactly hard, but you're going to have to use a product rule and a chain rule in this. So let's see if we can maybe make our lives a little easier by using logs. So what I'm going to say is I'm going to say natural log of y is the natural log of x times the square root of x squared plus 1. Now we know that from the log rules that this is natural log of x plus natural log of x squared plus 1 to the 1/2 power, because that's the square root, which is the natural log of x plus 1/2 natural log of x squared plus 1. So natural log of x squared plus 1. All right. Now what I can do is I can take a derivative of both sides. So I get y prime over y equals 1 over x plus 1/2 times 1 over x squared plus 1 times the derivative, which is 2x. So you still had to do it a bit of a chain rule here, but it's much cleaner. So now I get y prime over y equals 1 over x plus x over x squared plus 1. And I know what y is. Y is this. So I get y prime equals x times x squared plus 1 over x plus x for x squared plus 1. So that gets me square root of x squared plus 1 plus x squared over square root of x squared plus 1. And you could probably simplify that further, maybe, but I don't know that it's worth it. So you can do that, but you do that all without having to use a product rule or anything like that. And in this case, maybe it's not that big of a deal. But in this case, that's pretty ugly. Let's try to not do that. So again, this is positive because x is greater than 3. So we'll say natural log of y is the natural log squared minus 9 over x squared plus 9, which again, you bring out the 1/2 because that's to the 1/2 power. And then you can rewrite that so now we do the derivative. We say, all right, y prime over y is 1/2 times 2x, x squared minus 9, because it's 1 over this times its derivative, minus 1/2 2x over x squared plus 9. So what you have here then is we can simplify that. We can say y equals x over x squared minus 9 minus x over x squared plus 9, sorry, y prime over y. So then y prime is y times x over x squared minus 9, x over x squared plus 9. And we know that y is this thing, so y prime equals the square root of x squared minus 9 over x squared plus 9 times x over x squared minus 9 plus x squared plus 9. And you might say to yourself, why would you do that? Well, there's a couple of reasons, and a lot of it has to do with the fact that it's just easier. Like, it's more steps. It looks like more steps, at least, but it's easier. You don't have to think, okay, all right, I got to bring down 1/2, and then this thing to the negative 1/2 power. And so then once it's to the negative 1/2 power, then I have to chain the quotient rule here and just go on and on and on. Whereas this is just, okay, each step is simple. It may be more steps total, maybe, but each step is easier. So using logarithmic differentiation is really, the big key is in how much easier it is.